Since 2016, NASA's Juno spacecraft has been peering beneath Jupiter's beautiful but deceptive cloud layers, uncovering secrets that challenge everything we thought we knew about the solar system's largest planet. What mission scientists discovered deep within Jupiter's atmosphere defies explanation. A mysterious central storm system unlike anything found elsewhere in the universe. The data streaming back from Juno's sensors reveals that Jupiter isn't just a giant ball of gas, but a world harboring terrifying forces and unexplained phenomena that could reshape our understanding of planetary formation itself. The mysterious central storm discovery. Deep within Jupiter's core lies a discovery that has left planetary scientists speechless. Juno's microwave radiometer penetrated 350 kilometers below the cloud tops and detected what appears to be a permanent central vortex spanning thousands of kilometers across. Unlike the Great Red Spot or other visible storms, this deep atmospheric feature shows no signs of the typical cyclonic rotation patterns found elsewhere on Jupiter. Dr. Scott Bolton, Juno's principal investigator, describes it as a hurricane frozen in time, a massive atmospheric disturbance that appears to have remained unchanged for potentially millions of years. The storm system generates electromagnetic pulses that interfere with Juno's instruments, creating data gaps that suggest something far more complex than simple atmospheric circulation. Most disturbing is the storm's perfect geometric structure. It forms concentric rings with mathematical precision that defies known meteorological processes. The central vortex appears to extend all the way down to Jupiter's metallic hydrogen core, creating a direct channel between the planet's surface storms and its deepest interior regions. The beginning of the mission. Juno launched on August 5, 2011, beginning a 5-year journey to reach Jupiter and unlock the secrets of the solar system's formation. The spacecraft was designed with a unique polar orbit that would allow it to study Jupiter's interior structure without being destroyed by the planet's deadly radiation belts. Lockheed Martin built the titanium-armored probe to withstand radiation levels 1,000 times stronger than those that would kill a human instantly. The mission's primary goals included mapping Jupiter's gravitational field, studying its atmospheric composition, and determining whether the planet has a solid core. NASA scientists equipped Juno with 9 sophisticated instruments, including a JunoCam for public outreach and scientific imaging. The spacecraft's 3 massive solar panels make it the most distant solar-powered probe ever launched, generating electricity from sunlight 25 times weaker than that reaching Earth. After traveling 2.8 billion kilometers, Juno successfully entered Jupiter's orbit on July 4, 2016, beginning what would become one of the most revolutionary planetary exploration missions in history. Jupiter is the world of chaos. Jupiter's atmosphere operates on a scale of violence that dwarfs anything found on Earth. Wind speeds reach 640 kilometers per hour, nearly twice as fast as the strongest hurricanes ever recorded on our planet. The atmospheric bands that give Jupiter its distinctive striped appearance are actually jet streams containing more energy than all of Earth's weather systems combined. Dr. Andy Ingersoll from Caltech discovered that Jupiter's storms can maintain their intensity for centuries, with some features persisting longer than human civilization has existed. The planet's rapid 9.9-hour rotation creates Coriolis forces so powerful they tear apart smaller storm systems while strengthening larger ones. Temperature variations between different atmospheric layers create vertical wind shears that would instantly destroy any Earth-based aircraft. Most shocking is the discovery of thermal towers, massive columns of superheated gas that erupt from deep within Jupiter's interior, carrying energy equivalent to multiple nuclear explosions every second. These thermal plumes create the pop-up clouds that appear suddenly at atmospheric boundaries, representing eruptions of material from depths of over 100 kilometers below the visible cloud deck.
Io, the volcanic moon.
Io, Jupiter's innermost large moon, represents a world that's literally being torn apart by gravitational forces. This sulfur-covered hellscape hosts over 400 active volcanoes, making it, well, the most geologically active body in the solar system. Dr. Rosalie Lopez from JPL has cataloged volcanic eruptions on Io that blast material 500 kilometers into space. That's high enough to reach from Earth's surface all the way up to the International Space Station. Jupiter's immense gravity, along with the gravitational tugging from Europa and Ganymede, creates tidal flexing that generates enough internal heat to actually melt Io's rocky interior. The moon's volcanic activity pumps 1 ton of material per second into Jupiter's magnetosphere, creating a plasma torus that, feeds the planet's radiation belts. Some of Io's volcanic plumes reach temperatures of 1,800 degrees Celsius, that's hot enough to melt copper, while ejecting sulfur dioxide snow that gives the moon its distinctive yellow and orange appearance. Juno's observations reveal that Io's volcanic activity directly influences Jupiter's auroras, creating an electrical connection between the moon and the planet that generates 5 million amperes of current flowing through space. Research on Jupiter's magnetic field. Jupiter's magnetic field represents one of the most powerful and complex magnetic environments in the solar system. Generated by electrical currents in the planet's metallic hydrogen core, the field extends over 1 million kilometers from Jupiter's surface, so large it would appear 5 times the size of the full moon if you could actually see it from Earth. Dr. Jack Connerny from NASA Goddard leads research showing that Jupiter's magnetosphere contains enough energy to power human civilization for millions of years. The magnetic field traps charged particles from the solar wind, creating radiation belts that are 10,000 times more intense than Earth's Van Allen belts. Most mysteriously, Juno discovered that Jupiter's magnetic field has an asymmetric structure with a distinct northern magnetic anomaly, a feature that really shouldn't exist according to traditional magnetic field models. The field appears to be generated by shallow flows in the metallic hydrogen layer, rather than by deep convection processes as previously assumed. This discovery suggests that Jupiter's interior structure is far more complex than simple models predict, with multiple layers of conducting fluids creating a dynamo system unlike any other planet we've studied. Juno mission peaks under Jupiter's surface. Juno's gravitational measurements have, honestly, revolutionized our understanding of Jupiter's internal structure by revealing what actually lies beneath those swirling clouds. The spacecraft's precision tracking detected gravitational anomalies indicating that Jupiter has a fuzzy or dilute core, rather than the distinct, solid center that scientists had expected. Dr. Tristan Guillot from Observatoire de la Côte d'Azur analyzed the data, showing that heavy elements are mixed throughout Jupiter's interior instead of being concentrated in a central core. This partially dissolved core extends outward for thousands of kilometers, containing between 7 and 25 Earth masses of rocky material distributed through the planet's metallic hydrogen region. The discovery suggests that Jupiter suffered a massive collision early in its formation, an impact so violent it scattered core material throughout the planet's interior. Microwave soundings reveal that Jupiter's ammonia concentration varies dramatically with depth, creating distinct atmospheric layers that trap and release gases in complex cycles. The planet's interior rotates as a solid body down to depths of 3,000 kilometers, below which differential rotation creates shearing forces that generate the observed magnetic field patterns. Jupiter's formation and composition. Jupiter's formation story has been, completely rewritten by Juno's discoveries about the planet's water content and internal structure. Dr. Chung Lee from UC Berkeley found that Jupiter actually contains about 3 times more water than expected, with concentrations that, interestingly, vary dramatically between different atmospheric regions. The uneven water distribution suggests that Jupiter formed through core accretion rather than gravitational collapse, meaning it slowly built up from solid materials before capturing gas from the solar nebula. Heavy elements make up between 3 and 9% of Jupiter's total mass, far more than previous models predicted, which indicates the planet accumulated significant amounts of rocky planetesimals during its formation. The discovery of phosphine gas in Jupiter's upper atmosphere provides evidence of vertical mixing, which transports material from deep interior regions where the gas forms under extreme pressure. Isotopic ratios measured by Juno even suggest that Jupiter migrated inward toward the Sun during its early history before moving back to its current position, a grand tack model that helps explain the architecture of our entire solar system. This migration scattered asteroid belt material and prevented super-Earth formation in the inner solar system. Jupiter as Earth's protector. So, Jupiter actually serves as Earth's gravitational guardian, deflecting potentially catastrophic asteroids and comets away from the inner solar system. According to computer simulations by Dr. Kevin Grazier, without Jupiter's immense gravity, Earth would be bombarded by impacts 1,000 times more frequently, making complex life, virtually impossible. The planet's orbital resonances, create asteroid families and gaps in the asteroid belt, which prevents small rocky bodies from spiraling toward Earth. During the early solar system, Jupiter's migration scattered icy comets from the Kuiper belt, and many of those actually delivered the water that fills Earth's oceans today. The planet also captures interstellar objects entering our solar system, like asteroids from other star systems that could otherwise pose unpredictable threats to Earth. Recent studies show that Jupiter's gravitational influence extends beyond Neptune's orbit, affecting the trajectories of long-period comets that originate in the Oort cloud. But here's the thing. Jupiter occasionally sends objects toward Earth as well, since its gravity can perturb comet orbits and redirect them into the inner solar system. So, this double-edged protection means Jupiter both shields and sometimes threatens Earth, maintaining a delicate balance that has allowed life to flourish on our planet.
The Great Red Spot Mystery.
The Great Red Spot has been shrinking for over 150 years, and Juno's close-up observations are finally revealing why this iconic storm may be slowly dying. Dr. Amy Simon from NASA Goddard discovered that the storm has lost 50% of its width since the 1800s, and it continues shrinking at an accelerating rate. Juno's infrared spectrometer found that the Great Red Spot extends about 300 kilometers deep into Jupiter's atmosphere, much deeper than any hurricane on Earth, but actually shallower than expected for such a long-lived feature. The storm's distinctive red color comes from complex organic compounds created when ammonia and hydrogen sulfide are exposed to ultraviolet radiation from the sun. Wind measurements show that the storm's outer edges rotate faster than its center, creating shearing forces that may be gradually tearing the vortex apart. Most mysteriously, the Great Red Spot sometimes changes color from deep red to pale orange, which suggests chemical reactions are happening within the storm system. Computer models suggest the storm may completely disappear within the next 50 years, ending a 300-year-old atmospheric feature that has served as Jupiter's most recognizable landmark.
The Atmospheric Rivers Discovery.
Juno's microwave radiometer uncovered a previously unknown feature that might be Jupiter's most important atmospheric discovery: massive atmospheric rivers flowing beneath the visible cloud layers. These invisible currents transport ammonia and water vapor across thousands of kilometers, working like conveyor belts that redistribute heat and chemicals throughout Jupiter's atmosphere. Dr. Karen Dewar from the Weizmann Institute identified these deep atmospheric streams using radio emissions that can penetrate Jupiter's thick clouds. The atmospheric rivers flow at depths of 100 to 200 kilometers below the surface, carrying 10 times more material than all of Earth's atmospheric circulation combined. These hidden currents help explain how Jupiter's bands maintain their distinct chemical compositions, even with all the planet's turbulent mixing. The rivers seem to connect polar cyclones with equatorial jet streams, creating a global circulation pattern that operates independently of surface weather. Most remarkably, these deep atmospheric flows may be directly connected to Jupiter's metallic hydrogen core, suggesting that the planet's weather systems extend all the way to its center. This discovery really shows that Jupiter's atmosphere is a three-dimensional system, way more complex than the simple layered structure scientists used to assume. Juno's revelations about Jupiter have, honestly, shattered our understanding of the solar system's giant. From mysterious central storms to atmospheric rivers flowing beneath the clouds, Jupiter harbors secrets that challenge fundamental theories about planetary formation. The discovery that our cosmic protector contains a partially dissolved core and complex interior dynamics proves there's still so much to learn about our celestial neighborhood. So, which Jupiter mystery fascinated you the most? Share your thoughts below. If you enjoyed uncovering these incredible planetary secrets, go ahead and hit that like button, share with fellow space enthusiasts, and subscribe to Future Facts for more mind-blowing cosmic discoveries.